So, Sławek, the floor is yours.
Thank you very much. Thank you for the invitation. It's not clear to me why I'm a very important person since 2 years.
Well, I mean, in a sense, every person is very important.
Okay, let me show you my slides. Do you see the title page?
Yes, we do.
Good. So here you see the title, and as Paweł said, this will be about the famous problem, the reachability problem for Petri nets, whose complexity was a long-standing open problem, solved only very recently, and that's why I talk about it. So during this talk, I will mention several works. You see here a list of 5 papers. The authors are my colleagues from Warsaw, Wojciech Czerwiński and Łukasz Orlikowski, but also Filip Mazowiecki, Jérôme Leroux, and Ranko Lazic. So it's like a joint work of all of us, which resulted in finally closing this famous gap. Okay, so let's proceed. Some small yes. So I will divide my presentation into 2 parts. The first one will be about introducing the model and the problem, and explaining you what we know about the complexity of the problem up to now. And in the second part, we will try to prove something. In the most optimistic version, we'll maybe give you an overview of the proof of the most important recent result, namely the matching lower for the problem. But okay, I'll explain everything in the moment. Good. So the model we are working with is Petri nets. I'm not sure about the background you have, so please interrupt me at any moment, as long as you feel you want to ask me for explaining.
I'm afraid that we, at least some of us, do not know what are Petri nets.
Okay, good. So that's why I have this slide. So it's a nice model of computation which we can draw. Here you see a drawing like this. So what you see a bipartite graph, because there are 2 kinds of nodes. There are green circles and brown squares. These green circles are places. So during the computation, each place will store a number of tokens, certain undistinguishable items. So what counts is the number of tokens on each place. And now we have these transitions linked by arrows to the places. Say this one, it takes 1 token from place P and puts as a result 1 token on place Q, right? This is the semantics of arrows. Another one like this one takes a token from P and X. So in total 2 tokens, and also puts 2 tokens on P and Y. Okay, this is the meaning. Now the computation of such a net proceeds by just firing transitions as many times as one wants, and the choice of which one to fire is not deterministic. So there is a choice, potentially a choice between different transitions to be fired. Okay, and now we can speak about configurations. So a configuration is the information how many tokens is located on every of the places. Yes, it's like a vector of numbers. And the problem we will be discussing is about the reachability of a given configuration. Okay. So this is like an introduction to Petri nets, but this is not the definition I will use today. The model has several different but equivalent formulations, characterizations, or definitions. So quite often used one is oops, I have some small technical. I can maybe switch this off. Yeah, quite often used reformulation is so-called vector addition systems with states. So how I obtain this? It's basically an automaton where every transition is labeled by a vector, okay, of the same dimension. How do I obtain this lower automaton from the upper drawing? Okay, so observe that these two places P and Q are kind of special because the number of tokens stored jointly on these two places remains the same. If I take something from P or Q, then I also put something on P or Q, and it's always one. One thing is taken, one token is taken from P or Q, and also one is put back to P or Q. So these two places, they behave like a finite control state, finite control states. That's why there are these two states, P and Q, below. And now, if you organize the remaining places, X, Y, Z, into a vector of dimension 3, then you can describe succinctly effect of every of these transitions as a vector. For instance, the transition which this one, which takes a token from Q and puts on P, which means it goes from Q to P. Okay, what it does as an effect, it subtracts one from the number which is the number of tokens on Z. Right, it's this last coordinate here, and so on. So you can succinctly describe patchiness in this way. So now we are in the setting of automata which operate on some fixed number of counters. It's 3 counters here, okay, or operates with vectors of some fixed dimension 3 here, okay. And you can play with this kind of definition. There is a lot of other formulations which are pretty equivalent with respect to the problems I am discussing today. So you have, for instance, vector addition systems without states. They can be easily removed at the price of increasing a little bit the dimension. There is a model of automata with counters, but one important proviso: these automata are forbidden to test counters for 0 compared to 0. There is a way of rephrasing the model as a kind of rewriting, which is called ground multistate rewriting, and many others. For today's talk, I will take yet another perspective of this model. Namely, I will prefer to use the following syntax of so-called counter programs without 0 test. That's very important, and it can be understood, the syntax, as a syntactic sugar for vector addition systems with states. Like what you see here in this example program, you see like nested loops. You see an outer loop. This outer loop corresponds to the loop in the vase in the left bottom, which alternates between P and Q. And now you have 2 inner loops. Each of them corresponds to one of these 2 self loops in P or in Q. And if you look at the effects, if you look at this instruction here, which subtracts 1 from X and adds 1 to Y, it's exactly this vector on the left. Yeah, nothing happens to Z, to the third coordinate. And this outer loop has an effect only on Z, namely decrements by 1. Okay. Okay, so this is like an introduction, and now I'm going to formally introduce this model of counter programs. I'd like to stress that if you feel like asking me, just do it. Just don't hesitate to ask. So now I will introduce these counter programs a little bit more in detail to unambiguate the setting. Yeah. So as you've seen, it will be using counters. These are like variables that can store some integer value, but the value must be non-negative. It's not allowed to drop below 0. That's very important. If one allows dropping below 0, the model changes a lot. Analysis of this model becomes a lot simpler than this variant. Now, what's a counter program? It's just a sequence of commands. Okay, and there are just 3 kinds of commands. atomic commands, there is an increment and decrement. So you can add some fixed integer value to x, to a counter x, or you can subtract some fixed integer value from x. Okay. And now the only other kind of instructions or commands is a non-deterministic choice to go to line number L, or maybe to the line number L prime. So you choose one of these two options and you go non-deterministically. So the sequence of commands, the commands are numbered. And now important thing, non-negativeness amounts to saying that if the subtraction is executed for x which is not sufficiently large, the computation aborts. Okay, so this is one reason why the computation may abort and not complete, not to be completed. And now there is yet another kind of command which only is allowed at the very end, and it should stand at the very end of the program as the last command. It's a halting command or termination command. Okay, and now the program really halts or succeeds, but under the condition which is written here, under the condition that the specified counters x1 up to xl here are really 0 at the end. Okay, so in other terms, this is the only allowed form of zero tests. We can zero test, but only as the last step in the computation, only at this halting command. Okay, I hope it's clear enough. And now a small example. So we have this simple program here. We'll typically assume that we start with all counters 0, like here. All the 3 counters which are here used are 0 initially. And now, if you look at this small program, you see that there is a loop here. Namely, in line 2, we choose either we do the body of the loop, which is line 3, or we don't and skip immediately to the last command, which is halting command. Okay. Once we do a body in line 3, from line 4 we jump back to line 2. So it's a loop. So this program can be nicely described by the following syntactic sugar, like here. Okay. Oops, sorry. So I'll be using this sugar during all this talk. This loop construction has exactly the expected semantics, namely, it means iterate the body of the loop. The body is line 3, so these 3 commands, as many times as you want. Maybe 0, maybe positive number of iterations. Potentially, you can also loop forever and never go outside of the loop. Okay, that's the semantics of this syntactic sugar. And now, in this specific example, it's not possible to run forever because at every iteration of the loop, x prime is decremented by 1, which means that the number of iterations is at most 100 in every run. But note that there's many runs because the choice, should I continue my iteration in the loop or should I exit the loop, is done at every iteration non-deterministically, right? But among these 101 different runs or so of this program, there's only one which is halting, right? The one which iterates the loop exactly 100 times, and due to this, x prime is 0 at the end and the halt command is successful. Okay. So finally, we get these values of counters as a result. And essentially, my talk is about, so this is like something, it's this triple 0, 100, 300, 200 is like triple computed by this program, right? And essentially, the topic of this talk is to analyze how complex values can be computed by such programs, or how complex sets of values, sets of evaluations can be computed by such programs. Sets because there's not inherent non-determinism in the model. Okay. Last remark: we don't use zero tests. That's very important. If we do, we would be Turing complete. Okay, I hope this is clear. So now I proceed to defining the problem we will be mostly discussing today. It's the reachability problem. So as input, we get a counter program as defined above. And we ask if the program halts. So if there is at least one computation which successfully executes this last zero test in the halt command. Okay. This is the reachability. This is the variant of reachability problem I will be discussing. So as you see, the final configuration is partially specified because it's required that it's zero on certain counters, but it's left unspecified on the remaining counters. It's like partially specified final configuration variant of the reachability problem, which is easily shown to be equivalent to all other variants. And of course, it's not the only kind of question you can ask. And there is another one, which is from practical point of view, even more important. And from complexity point of view, much easier, namely the coverability problem, which is a special case where the halt doesn't specify any counters to be zero. It's like empty list in the halt command. So now what we care about in the reachability problem is just to get to the last line of the program, just to get without any test at the end, right? And this kind of this variant is called coverability. Good. So far, so good. I hear no question, so I happily go ahead. A short historical summary of the problem. I think it's interesting. So as you see, the timeline is quite long because the model and the reachability problem is investigated since at least 50 years. So the first result after introducing the model, which was done by Petri in the early 60s, I guess, the first remarkable result is the stability of coverability of the simple variant, right? It has been done almost 50 years, or more than 50 years ago by Karp and Miller. Then next important result is a lower bound by Lipton. It's 1976. It proves that coverability is X-space hard, so also reachability is X-space hard. But essentially, this proof shows that everything, any semantic question about Petri nets is X-space hard. So it's a universal lower bound, very nice construction. And now now I will be using two colors, green and red, for upper and lower bounds. So green means good news. We can do something in maybe this or that complexity. Red is bad news. It's as difficult as this, the problem, right? Good. So now I will mention a lot of results, but you will see that all of them are green. So about lower bounds, there was basically no progress until very recently. All the progress happened on the green side. Okay, so what was this? So in the 70s, this was a very important question. People studied a lot reachability, considering just the decidability status of reachability of the main variant. After the incomplete partial solution by Sasserbrot and Tenney, quite soon afterwards. Meanwhile, there is an X-space, so tight upper complexity bound for coverability. So at this moment, coverability is closed. It's X-space complete. That's it. We know everything. But still, the reachability has unknown status. And now, first decidability proof comes by Meyer in 1981. Then slightly simplified by Cosaraju. So people very often confuse these two and attribute everything to Cosaraju. Cosaraju just simplified the very complex construction of Meyer. So now we know, okay, it's decidable, but what about complexity? We know nothing. And then, of course, the main question became the complexity of the problem. And actually, for many years on, there was absolutely no progress. So as you see, the first next step is 10 years later. So there was no important progress meanwhile, But even this result by Lambert is basically the same proof. It's just optimizing, refining data structures. There's nothing really new. There is still just a decidability argument. No complexity. We know nothing about complexity except that it's decidable and exp space hard, the problem, right? So it's a huge gap. And like all these old results, they are jointly called KLMST decomposition. These 5 letters attribute this to these 5 people. And the composition is means in this case that the algorithm, given an instance like a Petri net or a counter program, it has several ways of simplifying the instance. So decomposing the instance into a number of possibly many, but slightly simpler instances. And this decomposition, this simplification proceeds until we get so simple instances which we can solve immediately. And the decidability arises from termination, from like well-foundedness of this process, but no one knew how long it can take. So how long are the branches in this decomposition tree? Okay, so this is what we had this time, and this stayed so for a quite long time. So you see, for the next 20 years, nothing really happened, and probably would never happen if Jérôme Leroux would not start working on Petri nets, because what he started doing was really a breakthrough. First step was to provide a new algorithm, different from this KLMST decomposition. Okay, the proof uses seminar invariants. It's nice, but from the complexity point of view, it's worth nothing, because this result based on 2 semi-decision procedures, so it doesn't give any better or just any estimation on the upper bound. So yeah, so there was a series of papers which resulted in a completely new decision procedure, but still no progress on complexity. And up to 2015, we knew nothing about the upper bound. So the first estimation was F omega 3. I will explain this F notation in a moment. It's a huge complexity, astronomical complexity, by Jérôme Leroux and Sylvain Schmitz, then improved a little bit, F omega. Okay, so at this stage, right, we have some progress on the upper bound, but we still know nothing about lower bound. And essentially, many people conjectured since a long time that, okay, maybe the problem is X space complete, like coverability could be so, yeah, why not? We don't have any good arguments against. We don't have an example where the shortest run would be more than double exponential. We don't have anything. We don't have a hard instances at all, right? So why not X space completeness, right? But actually, one could also think the opposite, namely, we are most often better in improving upper bounds, in designing algorithms, like people, human beings. But we are much worse in showing impossibility or hardness, right? So maybe this is the way. Maybe the way is to lift a little bit the lower bound, the X space lower bound, to profit from how reachability is different from coverability, to profit from some advantages here, like more expressibility here. And this happened. Actually, this happened in the same 2019. Absolutely surprisingly to all of us, there's a team of people involved. It's Wojtek Czerwiński, myself, Jan Kolarzyk, Jérôme Leroux, and Filip Mazowiecki. We found a gadget. We found a way of constructing a counter program where the shortest run is double exponential, triple exponential, whatever many exponential. Okay, which after some further advances yielded the tower lower bound. So then we knew, okay, the problem is not elementary. Yeah, it's quite hard complexity wise. And then maybe this could still stop for decades, but that didn't happen at all. And this gap announce like a new gap. It's of course compared to the previous huge gap, it's like nothing, but still between tower and Ackermann, there is a huge space. Yeah, it's still astronomical distance between these two bounds. Okay, so this could again get stuck, the problem, but it didn't happen. And quite not much time later, namely in last year, 2021, first indication that the tower is not the last word. Me with Wojtek and Łukasz, we found a way of kind of optimizing the tower lower bound. We profited from some redundancy, from some unexpected possibilities here, and we shown that the amount of resources which is needed for the problem is not tower, where the height is measured is roughly the size of the input, or say dimension of the input, number of counters, but the height is at least exponential in the number of counters. Okay, so it's not like a serious result, right? And it doesn't break the tower because it's still if considering tower as a class which is closed under elementary reductions, this is not any progress, but this is an indication that okay, it cannot be tower, intuitively speaking. Why? Because you can still imagine an algorithm which at every next counter, one more at every added counter to the programs, exponentiates the complexity, right? But now this would give this scheme of tower of n, but for tower of 2n, you would need to exponentiate the height of the tower, right? So I mean, you would need to double the height of the tower at every added new counter. Yeah, it seems like algorithmically kind of unsound. I mean, it cannot stop here. It must go further. And indeed, the same year, Wojtek with Łukasz, and independently Jérôme Leroux, like the same moment, they both these teams shown just Ackermannian lower bound. So this kind of ends the question. This closes the gap, right? And this result, which I will be discussing later, it's by elaboration of this tower construction, but it has also some new insights. So now the gap is closed, right? Since last year, the gap is closed. But okay, we don't like closing gaps. Yeah, once the gap is closed, we find another gap which is still not closed. One question is answered, we search immediately, get other questions which are still which can still be asked, and this happened also here. Namely, first I managed to improve a little bit the construction, which is not very important, but I'll explain you in a second what happened then. But for that I need a notation. I need a notation of this F complexity classes. Anyone wants maybe to ask about something at this stage? If not, that I will continue. So I'd like to introduce a family of huge complexity classes of some astronomical asymptotic complexity. For that, I need the shown here approximants of the Ackermann function, or the approximants for the consecutive levels of the Grzegorczyk, so-called Grzegorczyk hierarchy of fast-growing functions. So we start innocently with a function a1 which just doubles its argument. Okay, think of an argument as a positive integer. And now every next, like I+1 function in this family, what it does with its argument, it applies the previous one. It applies the ith approximant, right? But how many times? The number of consecutive applications or compositions is the argument. The argument decides how many times we compose the previous function. Okay, so it's n-fold composition of the previous approximant. Okay. To give you, most of you, I guess, are familiar with this approximant, but to give you some impression how fast the functions grow. So the second one is just exponentiation, but the third one is tower. So exponentiates as many times as the argument is. So the tower of n, the tower of exponents of height n. The fourth one would be a tower, right, whose size is a tower, a tower whose height is a tower, whose height is a tower, and so on. I need to repeat this n times. So it's a huge monster, but it's on level 4, right? And the Ackermannian, the Ackermann function is at the end. It's at the index omega. So to define even the Ackermann function, I need to use diagonalization along all these approximants, but we will not go there. I mean, I do not need this in this talk. So here, this is really very fast growing functions, right? And using them, I can define complexity classes, so classes of decision problems, where roughly speaking, the resources are bounded by these functions. So I will have complexity classes indexed by natural numbers, like here, like 1, 2, and so on. Here it is, this Fi class, right? So this Fi class, oops, I don't need this n on the left and on the right. Okay, I don't need this argument here. The Fi class contains decision problems which are solvable in deterministic time. Okay, but you could use, I mean, for large enough index I, like starting from 3, it doesn't matter if it's time or it's space. And now what's the bound on the resources is expressed by the AI function, clearly. And now you also precompose this A function with something which is of smaller order of magnitude. So you take this P from say the previous level. Okay, this is just for technical convenience to make this class close under reductions of from the previous levels, from the smaller levels than I. So for reductions given by functions from the level a-1. Doesn't matter too much, the details. Just remember that the complexity classes, these Fi classes, correspond to this. The Fi classes correspond to the AI functions, roughly. Good. Okay. And now to finish up with the history, I will using this F notation, I will be a bit more precise about the results. Namely, first, the upper bound, the Ackermannian upper bound, says that you can the problem when in dimension n-4, so when the n-4 counters, okay, can be solved in Fn, or if you have n counters, you can solve it in Fn+4. Okay, so it's roughly this. The level corresponds to the number of counters. This is the upper bound, and technically speaking, looking at the lower bounds, you get something similar, but still not tight. Namely, if you look at what dimension is sufficient to be Fn hard, okay, then the Czerwiński and Orlikowski, they show that in dimension 6n, so the construction uses 6n counters. Leroux uses 4n+5. My improvement, what I improved the Czerwiński and Orlikowski construction, it uses like 3n+1+2 counters. But the story is still not finished. There is a yet further improvement on this like dimension parametric complexity. So the newest construction by Leroux only uses dimension 2n+4 to get Fn hardness. Okay, so we can still ask what's the tight dimension parametric complexity, because there's still a gap, right? Like between n-4 and 2n+4, there is still a gap. We all suspect that there should be the coefficient should be 1, so there should be Fn hardness should be obtainable for n plus O of n counters, roughly n plus constant number of counters, but this is still not, we still don't know how to do it. So there is still a gap, right? So once you answer a question, you can always find another question to be asked. And it's not maybe as exciting as the main question, but it's from technical point of view, it's interesting. Yeah, how much optimized gadgets you can or instances you can produce for the lower mount. Okay, good. Can I go on? Because now I'm finished with the first part of the presentation. And I explained you the model, the question we asked, or we want to solve, I mean, the reachability problem. And I shown you all the complexities which are known by now with these recent results. And now I have a plan to shed some light on the proof. On its like more technical part. The main message is that it's not hard. It's quite easy to prove. Yeah, so you may be a bit frightened seeing all these F notations, complex, very fast-growing functions. Like you can expect a very technical development now, but actually it's not difficult. It's surprisingly simple. So I maybe will be even to explain you like the major parts of the proof. Okay, but in case you feel like not everything is clear for you, it's a good moment to ask before we really go to the technical part. Okay. Okay, so let's try to prove. Let's try to prove the result. So the objective is to prove FK hardness. Yeah, FK hardness. The number of counters we use is not very important. Yeah, I mean, it's 3K plus something, but it doesn't really matter. We need to construct a family of instances of counter programs which are that hard. Yeah, concerning reachability. Okay. So consider a counter program. Yes, initially all the counters are 0. Let's agree on this. But at the end, there are many possibilities because of non-determinism. So consider all the runs, all of them, which are successful, which end successfully the halting command. Okay, you get a set of valuations of counters. Let's call this set the set computed by a counter program. Okay, so I think of counter programs as computers, as devices that compute something, yield something at the end. It's a set of valuations. Okay, maybe infinite. Good. And now let's design something which would help us in the hardness argument. Okay, I will call this gadget B multiplier. So B is a fixed integer, fixed positive integer. That's a fixed number. Okay. Now it would be nice to have such a device where there are 3 distinguished counters B, C, and D. Okay. And there are many possibly many other counters, not so important for us. These 3 are important, very important. It would be very nice if we have a device that computes the following set. So I would like to have in B, in counter B, this capital B, this value, just this value which I request. Then in C, I would like to have possibly any positive value. So this means that there are many runs which are halting. For every possible positive number, there is a run which ends with C equal to this number, right? Because here I describe the set computed by the program. That's important. So I really need to be able to compute C equal to 1, C equal to 2, C equal to 3, and so on. Every possible value can be computed. And finally, the most important part, namely this multiplication here. Okay. So I want that one of these counters is equal to the multiplication of the remaining 2. D equals B times C. That's the most important. And now all other counters, let's say, let them be 0 at the end. Yeah, just for sake of easiness of argument. Good. What about this? I claim that if you have this kind of gadget, we can do a lot. I will show you in a moment. It's like easy to show hardness if you have this kind of gadgets. But okay, one can ask a question now, why B? Why do I fix my counter B to some specific number, capital B? Why not to have this, like multiplication, right? Would be even nicer to have a device which produces the multiplication triples, BCD, such that D is equal to B times C, all of them. Yeah, why not to compute multiplication? So this is probably not possible. Why? Imagine you have such a thing, yes? Then if you compute multiplication of two things, then you can also, by some simple adaptation, compute multiplication of three things or four things, or any number, fixed number of counters, okay? Which means that you can also compute values of polynomials, of Diophantine polynomials as a result in some of the counters, like counter D here, right? And then the reachability problem can be used easily to prove decidability of a problem which is undecidable, namely the 10th Hilbert's problem, the problem which, given a polynomial with integer coefficients, asks if there is an integer solution, integer zero, integer values where the polynomial is zero. So this is not possible, right? That's the maximum we can do, just fix B. We need to fix one of the B or C. And now a next doubt, okay, it's not a big deal. Here is a simple program which computes this, right? Look, what we do first, we put B to B, that's what we require. Then we also put B to D and 1 to C, and then whatever many times we increment C by 1 and D by B. You easily see that it's exactly the thing which computes the required relation, right? So what's the gain? What I want to gain here? So the important thing here is the complexity. If B is huge, say F7, okay? If B is a huge number, then the program here, the cheaper program I've shown you is also huge. But this is not what we want. We want to be able to to have this program small and also to be able to compute this program. And so here is the claim, which I want to assume, namely, for B, which is as large as this, okay? So whatever K and N are, this AK of N is something huge number, right? It's a huge number. It's very, very large. But here I claim that this big multiplier can be computed in time which is polynomial in K and N, in very small resources. That's the main message here. Not the ability or existence of such a gadget, but ability to compute such a small gadget, okay? Which has, by the way, not too many counters, but it's not that important. Okay, that's the main thing. And now let's assume conveniently that we have this. We magically can compute this huge multiplier. How to use it? And now it will be like an easy job, but still somewhere will be required. So to prove FK hardness, I need an FK hard decision problem. Here it is. So let's the input be a program which, attention, now can use zero tests. So it's like a full model. Say it will only use two counters. Okay, it's not the restriction in general, but they can be zero tested. And what we ask about, we have a variant of a halting problem, but a bounded halting problem. So we ask if there is a halting run under some bound on resources. Okay, the typical thing, which when you search for a problem which is hard for a class, you bound resources accordingly. And here I prefer to bound not the time or space, I prefer to bound number of zero tests. Just for convenience, it's not very important what you bound. It's pretty equivalent to other versions. Okay, and note that I divide by 2, which will appear later. Okay, it's all technical decisions. And now this is the decision problem, which is FK hard. I hope you believe me. And now how to reduce this to the reachability question. Okay, here's the reduction. So I want to produce efficiently a program without 0 tests, right? I want to get rid of 0 tests. And then the question would be, does it help? As I discussed before, yes, I want a reduction like this. So what I do, I take a copy of P below here, but this copy is instrumented in a certain way, which I will explain in the next slide. And this copy is preceded by the assumed huge multiplier. Okay. So this K and N comes from the parameter I choose here. It's about FK hardness. So K is some fixed number, and N is the size of the program we want to simulate, the program with 0 tests. Okay, and as I assumed, I have my AK of N multiplier. So I put it in front. What I know that it computes exactly the thing I need, this multiplication thing. Okay, so now this instrumented version of P, I only need to consider runs which start in this ratio of BCD and AK of N. Okay, in this multiplication situation. I don't care about runs which start in some other valuations. Okay, so I drop assumption that we start from 0 valuation. I will assume a set of initial valuations, exactly the set ratio of BCD and AK over. Okay, so this is this huge B, right, from the previous slide. I look at all the runs which start in these valuations of P. Okay, and I claim that I can make an instrumentation of P to be explained in the next slide, such that the program on the right altogether simulates faithfully the program on the left. But the program on the right, this P instrumented, will have no 0 tests as required. Okay, that's the point. So I trade 0 tests for the multiplier. So given a multiplier, I can get rid of 0 tests. Okay, how to instrument P to fulfill this task. So here is the set. Okay, the set of valuations we start with. Okay, so the 2 0 tested counters will be 0 initially, as in P, and otherwise we have this ratio valuations, exactly all these valuations. And I recall the aim is to correctly simulate like B over 2 0 tests. Yeah? B is this huge number here, the capital B. Okay, what we do. So first we add 3 new counters B, C, and D. Yeah, we should add it to P because they were not present before. And we get these initial values of B, C, and D. Yeah? So we add this. So this instrumented program has 3 counters more. Here you see why it's okay. 3 counters now. We'll get back to this, to counting of number of counters later. And second, more importantly, operations on X and Y, on the simulated counters, will be now instrumented as follows. At every increment of X, I add additionally decrement of C. At every decrement of X, I add additionally increment of C. And likewise for Y. Okay, what's the objective of this? The objective is to put these 2 counters, X and Y, like on a budget. So observe that by this instrumentation, they will never go beyond C. Impossible, because the C would have to drop below 0. I mean, they will never go above the initial value of C, which is, by the way, unbounded, arbitrary. So this is like fine. This doesn't really bound anything. Okay, But what it gives us certain invariant, namely this value never changes and is always equal to the initial value of C. Like X and Y, they eat a part of initial value of C. Okay. Now the most important part of the expectation, namely the zero tests. At every zero test of X, and it's also the same for Y, symmetrically, what we do, we put a piece of code like this, it's a macro, which is shown here. We discuss it later in the next slide in detail, but observe that at every execution of this macro, we decrease B by 2. That's why the number of zero tests we can simulate is B over 2, not B. Okay. But then we also decrease D. Look, there is a column which always decreases D. So D will go down and down and down. And at every simulation of zero test, it would decrease D by some amount. On the other hand, this thing remains constant. Look, every line, like subtract from Y, add to X, subtract from C, add to Y. Every of combination here preserves this sum. This is very important. Okay. Okay, so every zero test would consume 2 from B and a certain amount from D. And now at the end, what we do, most importantly, to the halting command of the program. It's, by the way, halting a list of P, but also of M, which can also have some halting command. We merge these two. But what we add here, we add a new counter, D, to the list. Okay, so D must be 0 at the end, which means that the simulation of zero tests should consume a lot, should consume like maximally, intuitively, to make D 0 at the end. Okay, if not enough of D subtracted from D, this zero test at the end will fail. That's the idea. Okay. Now, ignoring the rest of this thing, maybe that's not that important. I will explain you what's exactly this code that replaces a zero test. Okay, in the next slide. This is the most important part. This is like the core part of this whole instrumentation thing. Now we will see how it works, I hope. Okay, so what is this? I recall that we had constants value on the sums as C plus X plus Y, and that intuitively X and Y are put on budget C. Okay, so you see like 4 loops here. Okay, in each of these loops, what is going on? Always, every iteration decrements from D. So D is like paying for every iteration. But also there is a kind of flash. Like the first loop flashes from Y to X. Yeah? It takes from Y and puts to X, whatever many times, maybe 0, maybe more. But at most, maximally, the initial value of Y, right? Okay. So it can be shown like this. It can be described like this. So we flash from Y to X as much as we want. Maybe everything, maybe only partially. Then the next loop can be drawn similarly, but now we flash from C to Y. Again, maybe maximally, like everything, maybe only partially. Then the next loop, it goes back. So now we flash from Y to C back. So this 2 last loops, it's like flashing from C to Y and back from Y to C, right? Like a nonsense computational wise, but actually it makes a lot of sense for simulating a zero test. And as the last thing, what we do, we flash from X to Y. So we reverse the first loop. Okay. It's nothing like stupid flashing from some counter to another counter. But how many flashes happen? This is measured by the decrease of D, right? And at the end, we decrement D by 2. Good. So observe that while B decreases by 2 in every iteration, by what amount D decreases? That's a very important question. So if you analyze these 4 arrows on the right, you see that the first 2 arrows, they can maximally move this amount. It's impossible to move more, right? Likewise, the last two arrows also maximally transport this amount. It's impossible to transport more. Okay. But could it happen that they transport just this amount, this c plus x plus y, this invariant value? Could this happen? Yes, it could happen. But what are the circumstances? And now the key thing comes. The only case where this maximal transfer happens is when x was initially 0 and finally 0. So first, if this really happens, then indeed, assuming that y is transported maximally, c is transported maximally, and then back, all the transports are maximal, indeed we achieve this total amount of decrease of d, or amount of transport. Otherwise, yeah, otherwise we transport less. So we can distinguish now two cases. If the transport is maximal, necessarily we have x0 at the beginning and at the end of this macro. So also y is equal to c at the beginning and at the end of the macro. Okay, that's fine. So this is the correct simulation of the zero test, right? But what if the transport is not maximal? So it's less than this maximal amount. Now maybe x was not 0, right? So now it's a risky territory. What happens then? Yeah, how to assure a correct simulation of the zero test? And now the crucial answer comes. If this happens, that this initial invariant, assuming this initial invariant, is lost. Since b decreases by 2 and d decreases by less than, we end with greater than instead of equal. We lose invariant, we lose equality. Okay, what's bad with that? The bad is that we will never recover the equality. No way, because maximal decrease at every further simulation of zero test is this 2 times constant. But if we never recover, if we stay with greater than, then this is always positive until very end, which means that HALT will fail. So you see, we can cheat. We can transport non-maximally at every simulation. Imagine a huge number of zero tests, which is simulated by a huge number of these executions of these macros. At every single macro, we can cheat. But if we cheat a single time, we are lost. Namely, at the very end of the computation, we will fail. So the penalty will only come at the very end, right? But it will come ultimately. It will finally come. So the only halting runs are those which never cheat. That's the clue. Is it any clear to anyone? By the way, I'm not sure where we are. We go more and more into the technical stuff. I'm in the middle of the proof, so I've shown you half of the proof now. I've shown you how to proceed once we have this magic huge amplifier. Yeah? And the second part, which remains, is to show how to compute or to construct this guy, yeah, to this device, this gadget, how to compute it. So can I proceed, or there's an option also to stop at any stage. If you feel like you don't go into more detail, because there is yeah, a small amount of detail now. It's now easier, I guess. Once you know how to use multipliers by instrumenting programs with zero tests, then what's going on in the second part is again the same technique will work. Okay, so let me go further for still something like 15 minutes. So now I will define another type of programs which I will call amplifiers. Okay, so multipliers produce something at the end. It's something like constant value of b, fixed value of b. Amplifiers will be like functions we go one more level up. So amplifiers will start from some value and produce f of this value. F amplifier will look like this. Or here f is like the Ackermannian approximant. So starting from a value b, it will compute ak of b for every b. Okay, so I will introduce now the concept of the amplifier. And then the strategy will be to start from something very simple, like A1 is doubling, so this will be easy. This amplifier will not be hard to write down, to program. But then I will show a construction of lifting of amplifiers. So given an AK, I will go to AK plus 1. And this will be end of the story. Once I convince that amplifiers can be used to get multipliers, yeah, to this arrow also. Okay, so all these arrows must be explained, and also the concept of amplifier. Okay. So recall the notion of the set computed by the program, where we started from the initial single evaluation where everything is 0. Now, but you also see the cases when the initial evaluations were multiple, right? So let's now think of a set of evaluations, which are of initial evaluations, the whole set. And consider all programs which start in some valuation from this set. Okay, again, plenty of them, not only because we have plenty of initial evaluations, also plenty of choices, of non-deterministic choices. Okay, so we can now think of a set computed at the end from the set I of initial evaluations. Set computed from a set, right? That's the concept we want to use. And what we'll be looking at is the following thing. So we look at programs like this gray box here, which compute this set from this set. So both the input set and the output set of valuations, which will have the same form. It's a ratio of something, right? So I will use some free counters for the initial valuations to have ratio here, BCD. And I will use another three counters, B prime, C prime, D prime, to have this computed values. So this means that such a thing, such a program, which we call amplifier, has 6 distinguished counters, like 3 input counters, 3 output counters, and many possibly a lot of others also. Okay. And now, if f is a function from integers to integers, naturals to naturals, an f amplifier is such a program which computes from a ratio of b, ratio of f of b, whatever b is, whatever fixed b is. Okay, so I fix b first, but to an arbitrary value. It's unknown to the counter program, this value of b. Whatever b is, the program should manage to compute f of b. Yes. From b ratio, it should compute fb ratio. And as the last bit of detail, we see this d equals 0 here, namely, I want, for technical convenience, that the program, the only 0 test at the end, in the heart, is just d equals 0. D is one of these 3 input counters. Okay, just d must be tested, like before, like in the instrumentation before. Okay, and now the claim is that we can compute AK amplifier. Again, it has not too many counters. The computation is polynomial, blah blah blah. Right? There's no AK of n because now the parameter here is not a number, fixed number. It's just it's a function, right? Okay. So again, let's believe we have it, and let's see how to use this amplifier to produce a multiplier, which was promised before. Okay, good. Yeah, this d equals 0 is important for technical reasons. How to get multiplier from amplifier, like in the upper line here. It's very easy. The amplifier is like a powerful thing, right? It's the same AK. Given n in the beginning, yeah, it would be done. So it's enough to run our amplifier on a specific on the input where B is, this capital B is specifically chosen to be N. Okay. I recall that we compute from N and K this AK amplifier. Okay, so N is given in the. So we just instantiate this capital B to N. So also this is N according to the ratio. So which this means that we should have beforehand we should run something which we can call just N multiplier, right? But now N is given in the inputs, N is small. Now we can do explicit trivial, yeah, the trivial multiplier which you've seen before, which trivially computes, yeah. So N, a number N is small, we can represent it explicitly in the problem. Okay, so given this AK amplifier, we can like amplify our ratio to that large value. That's the idea here, right? And as a composition of these two things, we get this huge multiplier. Okay, good. So now the remaining thing is this: how to construct an AK amplifier. We start with K equal 1. This is easy. Here is a specific solution. I will not read this piece of code. You can look at the video later and analyze it on your own. It's by, again, kind of stupid flashing there and back a number of times to flash all of D to D prime, but doubling happens along this process. Nothing very interesting, boring, but the important thing is lifting. So given an AK amplifier, how to compute an AK plus 1 amplifier. This is the key part here, the key technical ingredient. Okay. So as a small technical remark, I will use slightly different approximations, which you see here. So the difference is that I have N over 4 instead of N iterations, one element, like also here you see it. But I start from 4, not from 1. Just for technical convenience, it's not important. These are equally good approximates. They are linearly related to the original ones, so not important. And now it will be easy, kind of easy. Okay, so I have this, given this AK amplifier, which has 6 distinguished counters. BCD with index 1 is input counters, and BCD with index 2 is output counters. Okay, I will bit out of it a new one, which will be even larger amplifier. I will use some small ingredients, like I will use 4 multiplier. This is exactly for this number here, as you can probably guess. I will also use something which I call identity amplifier. So identity function is like maps N to N. So identity amplifier given B ratio produces B ratio. So it like does nothing. Very important. But what's important here is its input counters are index 2 counters, right? While its output counters are index 1 counters. So if it works correctly, it just do a reverse of P, flashes back everything, right? So I want again and again execute P, which has this fixed B1, B2, B1, C1, D1 input counters. It's only for technical convenience. Now these are details. The most important thing is that what I do, basically, I just unfold the definition of the approximant here. Look at this piece of code which I see here. What it does. First, it computes 4 ratio using N. Fine, it's exactly this 4 in the beginning. Then it iterates a loop where the most important part is P. It's like AI. Yeah. Iterated a number of times, and then at the end in line 7, there is the last iteration. Okay. In between, I should flash back everything. So I use this L, which is identity amplifier, to like go back, right? How do I test if it's all fine, it's all correct? Now recall that amplifiers are guys which zero test at the end in the halt command, specific like D1 is tested here. That's why in the line 4 you see 0 of D1. So the piece of code I show you uses 0 tests. Likewise, L2 will 0 test D2 according to the definition of amplifier. Again, you see in line 6 the 0 test of D2. Okay, so it's okay. Seems like we are done, but okay, wait. We have 0 tests, right? Something we don't want to have. But now recall the instrumentation I introduced before. Why not to apply it here? It's a way of removing 0 tests, of getting rid of 0 tests. That's what I do now. I instrument this problem. The objective is to iterate the P iterated as many times as the argument of the function, as n, right? As n above, as this n here. Translated to the instrumentation, I see this value in the B counter in the beginning. So this BCD are newly introduced counters by the instrumentation, and they store the input thing, the input ratio, which is ratio n. If you look at the formula for the approximant, and it's this n. Okay, this n says how many times the P should be iterated. And recall that the instrumentation, the objective was exactly to do like B over 2 0 tests, something like this, yeah. Not B just, but B02, B over 2. That's why I use this 4 here and there to compensate for this. It's not very important. I basically do B0 tests. That's exactly what I want to do. I want to iterate the body of the loop, basically B times, yeah, well, the initial value of B. So to put it short, after the instrumentation, I get exactly what I need. I get a gadget which has no 0 tests and which iterates P as many times as is needed by the definition of the consecutive approximant. So I get the required AK plus 1 amplifier. And that's it. That's the end of the story. So you see, the proof is not complex. At least it can be like said in a short time. I'm not sure if it can be understood properly in so short time, but it can be succinctly explained. That's end of the technical part, and basically end of the talk. As the last word, I have like few remarks on mostly on what is still open, right? Because okay, after closing a gap, closing a problem, is it like end of the story? So my answer is no, it's not the end. There is a lot of very challenging and hard problems around. That's the main message. Except this gap, which is maybe not as exciting as like for everyone as for me. A very exciting question is, what about fixed low dimensions? So dimension 1 and 2 is very well understood. We know exact complexities. We know a lot. We know how reachability sets look like. There's a lot of results, but starting from dimension 3, we know nothing. No specific lower bounds, for instance. The lower bounds I present you make sense starting from level 3, so they apply to the dimension like 10 and beyond 10. So for the dimensions between 3 and 9, basically nothing known. There is some small progress for dimension 8. Like dimension 8 is tower hard according to some last news I got, but still there is the specific dimension 3. It's an extremely exciting question because it's a simple model. It's automata with 3 counters, no 0 tests. And we know nothing, absolutely nothing about the complexity of the problem. It's absolutely exciting and frustrating that we know so little about so simple model. And as a last point, the extensions of Petri nets, which are again very poorly understood and we know a little. All these 3 extensions mentioned here, they have open decidability status of the reachability problem. So for me, all of them are very interesting. It's either extending with data, so the tokens carry some data values that can be compared for equality, say, or maybe you add a push down to the VAS or to the Petri net. This specific variant of reachability has a lot of nice equivalent language theoretical formulations. It's very nice problem, but we know very little about the decidability of it. Only very special cases and only for coverability, I guess. Like dimension 1 and coverability is known and nothing else. And lastly, branching version of the model, posted in the setting of VAS when the run is a tree, not the line. So the run branches in the form of the tree. Again, we know decidability of coverability, but we know nothing about reachability except very small dimensions like 1. So yeah, it's all very exciting models and still need a lot of work, I guess. Okay, so I'm done. Thank you very much for the attention.